Hi, welcome back to Calculus. Today we're looking at section 3.10 in our book, Related Rates. So related rates are the story problems of the calculus world. Basically, the idea is something in the problem is changing, and it's almost always going to be changing with relation to time. So what we're going to be trying to figure out is, for instance, if you change the radius of a circle with respect to time, how does the area of the circle change with respect to time? So these problems really pretty much always come back to being derivatives with respect to time, because time is going to be our underlying fundamental here for everything. So I have some steps here. These can also be found in your book, maybe with a little more elaboration. But these are some steps that you can go through to try and solve these problems. And then we'll do like 3 examples of related rates problems. So this should be fun. So step 1, draw a picture and label it. We're going to use t for time, and all other variables are going to be assumed to be differentiable functions of t. So these variables are all going to be functions of t. So the radius of a circle, for instance, might be changing with respect to time. The area would be changing with respect to time. Everything comes back to t. Step 2, write down any numerical information you might have and try and use some symbols. So if you have a rate of change of the radius, then that would be dr dt, the rate of change of the radius with respect to time. What are you trying to find? An example would be something like dv dt. Maybe you want the change in the volume with respect to time. So we're going to have all this implicit differentiation that's going to go on to get us these pieces. You need to put together an equation. This can be very interesting and sometimes tricky. And step 5 then is to differentiate your equation with respect to time. So doing that, you're going to get a lot of these guys, a lot of these little implicit differentiation pieces that come out of it. And then we're going to plug in the information that we have to try and solve for whatever we're trying to find. So let's go ahead and take a look at a few examples. And yeah, hopefully this will go well for you. So let me get a new board. All right, so our first example fit nicely on the board, so I won't have to split the example in half. All right, so we want to find the rate of change in the surface area of a sphere if the radius is changing at 3 centimeters per second and the radius is 15 centimeters. Okay, so it makes a big difference how big that r actually is. All right, so we have here an equation for the surface area of a sphere. S is equal to 4 pi r squared. And again, note, s and r here are going to be functions of t. There's no t's in here, but we're going to treat them like functions of t. They change if we change the time. And so, first thing I did is I wrote down that dr dt, the change in the radius with respect to time, is 3 centimeters per second. So we actually had that as right here in our problem. And yeah, we see that it's changing. Now, so then I took the derivative with respect to t of this equation for the surface area. So the derivative of s was ds dt. I dropped the 2 down. 2 times 4 gave me 8 pi r. But then we're still doing implicit differentiation here. So we needed dr dt to come out of that r as well. It's that little chain rule tucked in there with that times the derivative of the r at the end. So now, once we're here, this is actually really straightforward. All I'm going to do is I'm going to plug in the 15 that we have for the radius, the 3 that we have for dr dt. I multiply everything out, and there we go. The change in the surface area with respect to time is 1,131 centimeters squared per second. Obviously, it's been rounded. There's no way that came out to a nice number with a pi there, but that's okay. So there we go. There's our first example. Let's do 2 more. All right, so my next example is going to take up more board space than I have, so unfortunately, you're going to have to pause here at some point, well, you're going to need to write this down, pause it, and then you can go on to the next bit of the video. So here's the problem. A 10-foot ladder is leaning against a wall. If the base of the ladder begins to slide away from the wall at a rate of 2 feet per second, how fast is the ladder sliding down the wall when it is 3 feet off the ground? So here we have a couple of really important things. You can see my picture here. I have a triangle. It is pretty clearly a right triangle because, well, at least we hope so, because we hope walls make 90-degree angles. And so that tells me I'm probably working with the Pythagorean theorem. where A, I'm making this side B, where B the side here at the bottom, B is the height of the triangle, and the C is 10 feet. It's the length of the ladder. Now, importantly, we have lots of things to label here before we go on to the next board. We know the length of side B because we're given that it's 3 feet off the ground. We know the length of side C. We don't know the length of side A. So we're going to have to actually use the Pythagorean theorem here probably to find that. We know how fast side A is changing. That distance from the wall to the base of the ladder is increasing at 2 feet per second. Now, kind of importantly here, it isn't going to play so much into this one, but the change of side B is going to be negative. That side is shrinking. This ladder is coming down the wall, and so the rate of change of side B with respect to T will be negative because, again, that side is shrinking. So we have all of this set up. We're going to need to find A. We're going to need to, and then we'll talk some more when I get the next board up. So let me get the next board. All right, so let's continue on. So first thing I did was I used the Pythagorean theorem to find the length of side A. Remember we said we thought we were probably going to need that. So I just did A squared plus B squared equals C squared. So A squared plus 9 is 100, filling in the 3 and the 10 for the B and the C. Subtract 9 and take the square root. Side A is the square root of 91. So then the next thing I did was I took the derivative of A squared plus B squared equals C squared. Again, we have sides that are changing here. They're all changing with respect to time. We needed a derivative, so I took it. So the derivative of A squared is 2A, and then don't forget the implicit differentiation piece, dA dt. The derivative of B squared, 2B, again, dB dt. And the derivative of C squared is 2C dC dt. And now you might be asking yourself, well, I can see where you've got all of this information except the dC dt, right? We have A, we just found that. We were given B as 3. We know that dA dt is 2 feet per second. We know C is 10, but what the heck is dC dt? Now let's go back to our picture. Side C is the ladder. The ladder is 10 feet long. We're going to assume that this ladder is not changing its length. Okay, maybe it's an extension ladder, so maybe it could change its length, but let's just assume that it's not. So dC dt is actually just 0, meaning this whole right-hand side turns into 0. So then I cleaned it up a little bit. 2 times 3 is 6, so I have 6 dB dt, and then I did 2 times 2 to get 4, and I subtracted it and brought it to the other side. It's negative, so it's equal to negative 4 squared root of 91. Divide both sides by 6 and throw it in your calculator, and you get the dB dt is equal to negative 6.4 feet per second. So yeah, that's moving. Anyway, so there we go. There's our change in the length of side B with respect to time. All right, so I have one more example to work through, so give me a minute to get on board. Okay, so I have another great big example. Again, you're going to have to sit through this board, get it all written down, pause it, and then I'll pause it. And then when I come back, we'll finish up the problem. So it says coffee is draining into a cylindrical coffee pot with a radius of 3 inches at a rate of 10 inches cubed per minute. Now I want to pause there for just a second and point out that this rate is a change in volume. Right? The coffee is coming in, that's filling up space, that's a change in volume. So the change in volume is 10 inches cubed per minute, and we'll get to that over here. The question asks, how fast is the level of coffee in the pot changing when the coffee is 5 inches deep? Okay, so it really doesn't matter here how tall our cylindrical coffee pot is. The only thing that matters is we know how deep it is when we're looking at the rate of change for this problem. So I'm working here with the formula for the volume of a cylinder, pi r squared h. And you'll notice I have everything laid out for us. We know dV dt, the change in the coffee, right? That's the change in the volume, is 10 inches cubed per minute. The radius is 3 inches. The height is 5 inches. We're given both of those. There they are. dr dt is 0. You have a coffee pot. It is not expanding out. Okay, the coffee is coming up in that pot, but the radius can't change. So dr dt is going to be 0, and dH dt is what we're going to try and find. So give me a minute, I'll erase this, and then we'll take this derivative and plug in all the pertinent information. Okay, so you can see I took all the information and left that here so that we could plug it in over here after we did our derivative, our implicit differentiation. So I took the derivative of the v equals pi r squared h. Please note, again, we have a product rule here because of the implicit differentiation. R and h are both considered to be functions with respect to time. So we have a product rule. That's why you can see I have a plus sign here. So the derivative of v is dv dt. We already know that that's 10. So for the first one, I took the derivative of the r squared. So I got 2 pi r. I just put that 2 all the way in front. I have the h. But again, since I'm taking the derivative of the, basically of the r piece of that, I have to have a dr dt. Plus, this time the r squared just stays put. It's not going anywhere. That's the one that we leave alone for this after the product rule. So we have pi r squared. Derivative of h is 1, but don't forget the dh dt. So there's my product rule. It's kind of a big and it's a mess. I plug everything in. 2 pi, 3, 5. 3 is r, 5 is h, but dr dt is 0, which is nice. It makes all of that go away and turn into 0. R is 3, so we get pi times 3 squared times dh dt for 9 pi dh dt. I divided both sides by 9 pi. We get 10 over 9 pi, or about 3.5 inches per minute. So there you go. Those are related rates. Just remember, any letters in the problem are probably functions of time. Some of them will have rates of change that are 0, and that's nice. It makes things a little bit easier. But everything when you differentiate is going to have a dr dt or a dh dt because everything is a function with relation to time. So thanks for watching. Have a wonderful day.